So if we just assume that we have like a simple regression with just one x variable, we can show these that the slope parameter is consistent fairly easily. So let's say, for example, y equals beta 0 plus beta 1 x1 plus u. So let's just look at a simple regression and kind of show that beta 1 hat is going to be a consistent estimator of beta 1. So if we remember our formulas, our beta hat 1 would be the sum of yi minus y bar xi, I guess x1i minus x1 bar, over the sum of x1i minus x1 bar squared. But remember, this was mathematically equivalent to the following, and we're going to use that fact just to make things a bit easier. So remember, instead of just having one of the bars, we can just have y, and we showed before why that's mathematically the same, even though it looks a bit weird that it's the same, but they are if you expanded the sums. All right, so now what we're going to do is we're going to plug this identity for yi into there. And so that's going to give us that beta hat 1 equals the sum of x1i minus x1 bar times beta 0 plus beta 1 x1i, right, just plugging that in, plus ui. And everything, again, is still over x1i minus x1 bar squared. So I just replaced this yi with this term here from our regression. And let's start dividing, kind of multiplying through. So we'll multiply this first bracket by beta 0, then we'll take that first bracket, multiply it by the second term, and then that first bracket, multiply it by the third term. And we're going to start separating or breaking up this fraction here as well. All right, so it's going to get a little bit uglier, but hopefully we can see what's going on. All right, so this first bracket times this first term, well, beta 0 is a constant, right? So we can take it out of the sum. So now we have beta 0 times the sum of x1i minus x1 bar over the sum of x1i minus x1 bar squared. So that's that first term. We're going to deal with that in a second. Then we have this second term. Again, we're multiplying this by this. Beta 1 is a constant. It's the true value, so it's just some value. We don't know it, but it's not random. And now in our brackets, we have x1i minus x1 bar times x1i over x1i minus x1 bar squared. And we're going to again think of using some kind of trick like we did, not trick, but mathematical equivalent of this, kind of like what we did up here in a second. And we have this final term. So we have the sum of x1i minus x1 bar times ui over the sum of x1i minus x1 bar squared. All right, so now we can cancel a few things out. So the first thing to notice is that this term here, hopefully you can make it out, is 0, right? Adding up all the values of x1 and then subtracting n times the mean is going to be equal to 0. So we've kind of seen that this is equal to 0 before, so this whole first term is going to drop out. Now let's think about the second term. Just like kind of like what we did here, an equivalent of way of writing this denominator would be something like this, and we'd have the same thing. We didn't do that there, but it's equivalent in terms of, it's mathematically equivalent. So that means all these things are going to cancel out. So now we have the true value, and then we still have this final term kicking around here. So hopefully that, what I canceled out, kind of made somewhat sense to you. It's a lot of stuff we've seen kind of before, it's just putting them all together at once. So here, maybe I'll put a little 1 and a little 2. So 1 is using the fact that the sum of x1i equals n times x bar, and the sum of negative x bar 1 equals negative n times x bar. So that means these are going to cancel out once you break up the sum there. And the second thing that's happening here is that mathematically x1i minus x1 bar times x1i is the same thing as x1i minus x1 bar squared. Just mathematically they're the same thing. Or I mean, we could even do it in 2 more steps. In case that's not clear, so these are kind of the two, two things we use to kind of break down this kind of green equation into this, hopefully it comes out a little bit, but this orange equation down here. And so this is kind of where we're stuck, or not where we're stuck, but this is where we're at. And so let's erase this board and then we'll start working from here. All right, so this is where we got to before, I guess this was a j. Beta had j, oh, it was a 1 actually, since we just had 1. X, so beta hat 1 equals beta 1 plus this amount. x1i minus x1 bar times ui over this, the sum of x1i minus x1 bar squared. So that's that last line that we kind of had down here. And we had the explanation of how we got there kind of down here, I think somewhere. All right, so let's think about this second term. So let's multiply this second term by 1. But let's multiply it by 1 by multiplying the numerator and the denominator by the same thing. And that's going to be 1 over n. So beta hat 1 equals beta 1. We're going to multiply the numerator by 1 over n and the denominator by 1 over n. So it's not changing anything about this fraction, right? We're just essentially multiplying by 1. But it's going to allow us to think about using the law of large numbers. All right, so if we think about what the numerator is, so we're going to use the law of large numbers on this. So let's think about what the numerator is. 1 over n times the sum of x1i minus x1 bar times ui, and you can imagine that there's a u bar here, but that just happens to equal 0. Well, this is the equivalent, or this is by definition, the covariance, I should say, between u and x, or between x and u. Right, just mathematically, that's the covariance. And if we think about, and I'm missing a squared here, but if we think about this denominator, this is by definition the variance of x. And so as n goes to infinity, so this is as n goes to infinity here. So the probability limit, if you remember that from the review of stats module, it's the limit in probability of beta hat 1 approaches the true value of beta 1 plus this covariance of x and u over the variance of x. And here it's important that we're going to make sure we mention these are about the population, not the sample. So we're using the fact that n goes to infinity here. So that's how we're getting these. It's like the population covariance and the population variance. It's not about the sample because we're using n goes to infinity. So these things are the population variances, and the population covariance is not the sample. And this is going to be equal to 0 by our assumption about the expectation of u given all the x's, right? There has to be 0 covariance. And so that's how we get that the p-lim of our beta hat 1 is equal to the true value. So we're getting this consistent estimator. In reality, we need a couple more kind of assumptions. Other assumptions we kind of needed there. We had to make this, we made the assumption that the variance of x was less than infinity. So not only can it not just have one value, not only do we need multiple values of x to estimate this regression, but in order to derive this, we need the variance to be less than infinity. And we also need the variance of u to be less than infinity as well. All right, so here we just showed that the OLS estimator, the slope parameter anyway, was a consistent estimator. We just did a little bit of algebra to get down to this point here. Then we multiply both the numerator and denominator by 1 over n, so it doesn't change the fraction at all. And then we're thinking about what these equations represent, and the first one is the covariance, and the second, the denominator, is the covariance of x and u, and the denominator is the variance of x. And as n goes to infinity, they're going to approach their population covariance and their population variances. And I just want to make that clear. It's not that the variance goes to 0, it's this whole fraction is going to 0 by assumption, or equals 0 by assumption, because of the assumption we made about the covariance between x and u. And then if that assumption holds, this covariance equals 0, then the p-lim of beta hat 1 is just equal to the true value. So that means it's a consistent estimator. And I just kind of mentioned a couple other assumptions we needed to make. This can't be infinity, and the variance of u can't be infinity as well.